Okay, Xianglin. So in this case, we can briefly recap uh, what how the content or the outline of your presentation. We are not actually record a video.
So basically, it's about to recap the last experiment of every average causal effect paper, and also to explain the 5 properties um, that the attribution method should have, and then we can go through the gradient integrated gradient and average causal effect one by one and see if they satisfy that those 5 properties or not. Yeah, so basically that's it. And remember last week when we talked about the last experiment of average causal effect, and here they train their model on uh, uh, on beta VAE. So what beta VAE is? First, I think we need to know what VAE is. So the goal of VAE is to um, project your data space into some latent space and then use a decoder to reconstruct the data set. For example, if your model is trained on photos of human face, then those latent space might capture some features of human face. And in this way, the decoder can use those information to reconstruct the data set. But somehow you don't know each dimension in the latent space means. So that might contain, each dimension might contain a lot of features information. So what beta VAE tries to do is to disentangle those information. So the latent space in beta VAE, each dimension can represent one single generative factor. So for example, if your beta VAE model is trained on human face, then they would make sure each dimension will represent, for example, like the skin of your color, or the gentle or gender, or for example, your expression, whether you are smile or you are crying, those kind of information. So each dimension in the latent space would only represent one generative factor. So I wouldn't explain the details on how they do that, but um, here you would know each dimension will only represent some features. So here they train the beta VAE on means data set. So basically, what they do is, what they do is, um, the, the latent space contains 20 dimensions. So the first dimension is 10 discrete variable. We denote it as C0 to C9. So C0 represents for class digit 0, and C1 represent for digit 1. And also they have 10 continuous variables. They denoted as C0 to C9. So they only know those variables controls the rotation or scaling factor for those digits, but they don't know each one of them would represent for what. For example, if for Z0, we only know that it controls the rotation or scaling factor for some digit, but now when we train the models, we don't know which digit it controls. So here you can see the
Z0 can control any. So the point is that so you have C1, C0 to C9, and
they represent for
Z0 to Z. Yeah, I understand. C9. So assume that this Z0 is 1. It means that you're going to generate a digit with the shape of 0.
Can you be louder?
Okay.
Yeah, okay,
If the dimension of C0 is 1, so I just raised it for example, it means that it will generate a digital of with shape of 0. Is that correct?
Yeah, so C0 would be 1 and C1 to C9 would be 0.
Okay, so what if, so I have a few questions here. And what if C0 and C1 are both 1? So what is going to happen?
So in this network, in the beta VAE, it wouldn't happen. So you would only have
so
one.
it is actually a legitimate. It is not a is a illegal, illegal embedding. So that means the one from 0 to 1, the digital, the dimension from C0 to Z9 are actually exclusive, right? So the sign 1. And now explaining the 0, and you mean I still have confusion about, you mean for Z0 we do not know and what will be rotation. So 0 maybe means a rotation. We need to rotate the digit a little bit. So in the case that they C0 and C dimensions and the D dimensions are orthogonal. Orthogonal means that given a number C and choosing, and also may I ask from C0 and Z9, and are they exclusive? Means if we enable means that we set the 0 to be 1, or 0 is the continue. Oh, you mean that 0 is Z is actually continuous?
Yeah, Z is continuous, and
so what's the range? Do you know what's the range? 0 to 1 or 0 to
you mean the range for Z?
Yes.
I think it's from most of the Z range from -3 to 3.
Okay, so I have a range. So whatever -3 to 3, if we just do a linear
it follows the
transformation,
three sigma
distribution, right?
Yeah.
And somehow conform to whatever. So we have a range. It's good to know we have a bound. We have upper bound and the lower bound. So Z0 to Z9 is not supposed to be an exclusive. For example, Z0 could be 0.5 and C1 could be 0.3. It is possible, right?
Oh yeah.
It's possible. So given that Z0 and Z dimensions actually is just it's just controlling the shape. So it seems that Z and C are also orthogonal. So whatever C is, suppose it's 1, C, suppose it's one digit of 0, digit of 1, digit of 3, whatever it is. So given a digital, given an arbitrary digit, we can always compress, rescale, or rotate it. So here, what do you mean that we don't know what Z is going to do?
I mean, you don't know. For example, here C0, you don't know which digit it controls. So you can get that from B, C, D rows. So in the row B, they set the CA to be 1, and
CA to be 1. Okay.
So from row B, row C and row D, actually they set the CA to be 1, and then B.
CA to be 1. What do you mean by CA to be 1?
That means the digit will be 8.
I mean CA.
Oh, so here actually they
You mean CA to be 1? Okay.
So remember when we talk about the average causal effect, we change the input the value for some inputs and see the expectation of the output. So here our input would be C and Z, and the output would be each pixels in the output of decoder.
Okay.
So that means they wanted to know if you set, for example, from row A, they set the C, the first image in the row A, they set C0 to be 1, and observe the average causal effect on each pixels in the output. So this way they will know if you set C0 to be 1, then the red ring would have positive average causal effect. Yeah.
So the first row means that if we set Z0 to 1 or 2, if we see the C1 to 1, it means that
C0 to 1, and the second image will be set C1 to
1. So
yeah.
so those those pixels are what ACE is calculated. It's going to be calculated. Okay.
Yeah.
So let's come back to the previous statement saying that we don't know what the C0.
So in the row B, they set CA to be 1 and interval Z0. And
okay, so this is 1. This is going up to 0.
You see here, so the row B is they set CA to be 1, so it's digit 8. And then they change the value of Z0 and observe the average causal effect on the outcome. And on the row C, they set the CA to be 1 and observe and change the value of Z6. And in this way, B and C, B row and C row seems quite interpretable. However, for D, it looks like a mess. So they say Z0 and Z6 would be the factor to control the rotation and scaling for digit 8. And however, for other Z, they have no relation to digit 8.
Okay, so let me rephrase. I somehow get your point now. So the point is that, so here there's this is beta VAE. So despite there's a VAE, we can just think about this is decoder, but it's a very specialized decoder. And they have actually 20 dimensions as the input of decoder. So and this is the decoder here, summarized here. This is decoder D. And the first half of the input, maybe the first 10 input is about represent the class. The class range from 0 to 8, 0 to 9. So each dimension mentioned what digital we're going to generate it. And Z is actually this part which is a bit tricky. The tricky part is that Z, the dimension Z is control how to generate a variance of a specific digital. Suppose we let C0, suppose we let C0 to be 1, and the Z is going to control what is the shape of the 0. The 0 could be like this, the 0 could be like this, and the 0 could be like this. Anyway, so they have a lot of variance from zeros. But the point is that some dimension of the Z can control some digitals. We do not know, we never know, maybe, but with their approach, we can know. But after we train it, we never know which Z can control which Z. So the point is that maybe Z1, Z0 and C1 can control the shape of Z, can control the shape of C0. Maybe the Z9 can control the shape of C8, 8. But it is possible that the Z9 is not relevant. It's irrelevant to the shape, to control the shape of or change the shape of 0. So the goal of this work or this experiment is going to show that whether this approach called the CAE can decide or find the causal relation of Z and C. That means what Z can control the shape of what C, right? So this is
that's the point. So so their experiment basically try to explain the decoder of beta VAE. Yeah.
Okay, I think now it is quite clarified here. So Xianglin, have you prepared some questions here? I think it's better to prepare some questions for the audience. Yeah. Maybe we can ask a very naive questions. you can see.
I think.
So let me raise the questions. Here, maybe Xianglin can correct me because you are the one who read the paper.
Okay.
I'm the one who have a second-hand knowledge from you. So maybe I raise the questions. Maybe I'm still a little bit confused about the answer, but I have the questions.
Okay.
So is that possible? All the Z dimensions can control the shape of V1. So maybe we can ask a student to answer this. Maybe Wang Chao, can you answer this question? Hello, Wang Chao.
Did Wang Chao listen to my presentation last week?
Okay. So how about Zheng Feng? Hello, Zheng Feng. Maybe Ruofan. The question is that
possible.
It is possible.
Yeah, according to the definition given by Xianglin, we only restrict each Z as it only represents one kind of rescaling factor, but we don't limit.
But if you only control one digit, then how can you for example, if all the Z controls digit 0, then the C1 to C8 or C1 to C9 generated by the decoder would be the same because they only get the information from C1 to C9, right?
So one Z can only control one C, is it?
I mean, I don't think it.
Yeah, here are the tricky questions, but I think we do not linger on here on this problem too much because it's not our focus. So here the interesting question is that one Z can control multiple C?
Oh, one Z can control multiple C, then no.
It's no, right? Only one Z. So that so in this case, if one Z can control at most one C, maybe one C. So in this case, in your case,
oh, you mean
both
okay.
both Z0 and Z6 can control C8. That means there must be one C which cannot be controlled by any Z.
Oh yeah, that's right.
Okay, maybe that's the question. That's the question out of the Okay, I think let's move on this part. I think this point has been well clarified.
So, those are the results. Maybe we should first go through what the three attribution methods are. So the first one is gradient. So suppose here we have a vector x with n random variables from x0 to n+1 random variable from x0 to xn. And we have a baseline x prime from x0 prime to xn prime. And the attribution method would be how much influence x would make on the fx. So the gradient method is just the partial derivative of function f with respect to each xi. And for the integrated gradient method, they assume there's a path between x and the baseline x prime, and they try to find each dot in the path and compute the gradients for each dot in the path and sum them up as an integrated gradient. And average causal effect would just be I explained it last week. So it would be the expectation of output y when you intervene some xi to be alpha, and then minus the expectation of y of the input baseline xi.
So for ACE, it will have a baseline of it. So the baseline for so both integrated gradient and ACE. So what's the full name ACE? The accumulated or?
I think I look into.
I mean, what's the full name of ACE? I forgot.
Average causal effect.
Okay, yeah, average causal effect. For both integrated gradients and ACEs, they were using a baseline. They use baseline. The baseline for integrated gradients is actually input.
Yeah.
And the baseline for ACE is actually an expectation.
A what?
An expectation. The baseline xi.
No. The baseline xi. We know the baseline xi, but we still need to calculate the expectation of y if you set the xi to be one baseline xi.
Yeah. I'm saying that the baseline xi is the expectation of y.
Oh yeah.
I'm saying the baseline of AC is the expectation.
So they mean when they write it in baseline xi, they are saying that you can choose whichever baseline based on perhaps some domain specific knowledge. But here they can use, for example, the average of xi in all the training data set. But you can actually choose one for yourself. So maybe for example, for an image, the baseline might be a white.
You are talking about the baseline.
How to choose baseline?
You're talking about the baseline of the both integrated gradients and ACE, right?
I'm talking about yeah.
Because both one, they always need to find a baseline of an x prime or xi prime. So this xi prime, yeah. So this xi prime is somehow equivalent to alpha. Yeah, it's equivalent to alpha.
Alpha.
Is that right? So
I think alpha is your let me enter.
I mean here, because we can we
no
can we use this alpha into A? Maybe we'll change the name of A, because so this this is
no.
I think I'm not correct. Yeah, you're right. So please go on.
So the x prime is the baseline. So this one is the baseline, and here we have baseline here. But alpha is our input. So the alpha is equivalent to this xi. So we have one input and one baseline.
So somehow the integrated gradients and ACE share the same input, almost share the same input. We have a baseline xi prime.
Yeah.
And we would like to know, assuming assuming xi equals alpha, we're going to see whether
so here is alpha. Also, this alpha comes from maybe you can change it to beta. What is not relevant.
Yeah. So this xi. So here it's going to this attribution method is going to explain when xi is equal to alpha and
how far it would be from the baseline xi.
Sorry. So when xi is equal to alpha, what's its impact on the final? What's its causal impact on the final output of y? Am I right? So anyway, we need to calculate. So this f is equal to y. Y is the value of f. So whatever it is, so given xi equal to alpha, and this xi is equal to alpha, we're going to see that when xi is equal to alpha, and what's its impact, or what is the causal effect because integrated gradients is still a causal effect, right?
Yeah.
And what's its causal effect to the existing y?
Yeah.
Yeah, because so let me illustrate about integrated. So do you have any slides to further illustrate integrated gradient?
No more. Just
okay, maybe I can conceive a little bit, and then maybe in the meantime we can digest this together. Of course, maybe Xianglin, you have your own insight. You can complement me if I'm missing something. So let's take a very simple effect of y equal, let's say, suppose this is y and suppose this is x. And somehow we would like to see, so this might be the shape of y, right? So this is the shape of y. And then for this shape, and then when we calculate the gradient here, we find the gradient here is almost 0, right? And suppose here is an alpha.
Oh, actually, I have this example.
Okay.
Yeah, I drew a picture here.
Okay, that's great. Let's see your picture.
Yeah. So, what are you trying to say? You are trying to explain integrated gradient.
Yes, I'm going to try to digest or think deeper about this integrated gradient.
So let's assume there's a straight line between x and x prime baseline, and what they do is for each dot, is that right? Dot in this line, they calculate the gradient for each dot and sum them up as the
I see. So is that integrated? So you are using the integration operation for. So is the integrated gradient is area of this shape. So if I remember correctly, so here x minus x prime, and it will be calculated with between x
0 to
and x.
here is
Sorry, it's 0 to 1. 0 to 1. And it's going to f x prime. And sorry, let me check. I forgot it.
This equation.
So it's calculated the.
So x plus alpha times x minus x.
What does this x here? So this x is this x
input.
So
x. So imagine there's a line like this. This is x. This is x. X prime, and x plus alpha times x minus x prime would be
in the middle. Right?
Yeah, in the middle. So you rate the range of alpha is 0 to 1. So like you are each time you come here, like for example, this would be the alpha. Not alpha means.
This alpha is a very small part of the alpha. I think it's this is alpha. Alpha is 0 and to 1. And it's going
to like from start. It starts from x.
So the question I'm going to ask is that when it will calculate, it will. So if that means that suppose the shape of f is look like this, is this integration means that the area of this is for the under the curve. Are you under my point? So here is a.
Yeah, I get your point. I think then this line should be the derivative, the partial derivative of f, not f.
Yeah. So in this case, when the variable is we are not using multiple variables, single variables. So the area, I think, so if we union area is supposed to be f x dx, right? So a and b. So that is supposed to be the this is integrate. This is the formula to calculate the areas under this region, right? And I think this almost exactly the same. Am I correct, Rohan?
But here is actually summing up all the gradient, not the integral.
Yeah.
Yeah.
So it's not. It's, oh yeah. Yeah, you're right. It's not the area. So you're correct. It's not the. So it's more like the average gradient, right? It's more like an average gradient.
Yeah.
And then is that to divided by x minus?
Divide what?
Is so here I'm thinking about here. So it was times the term x minus x prime. The term x minus x prime.
Oh yeah.
And the okay, please go on. Let's take Xianglin's examples to understand more details. Maybe you can cut these formulas a little bit so that we
Cut
can
what formula?
these formulas a little bit. So let me digest it.
So like they assume there's a path between x and xi, and like for each point on that path, they calculate the gradient.
The gradients.
Yeah, and then they
sum together. They sum together, and then
times the length of the path.
Times the length of the path, right?
Yeah. Yeah, because here they just assume there's a straight line between xi and xi prime. So then after you get the integrate gradients for each random variable x.
So I'm thinking about what's the physical meanings of these paths. So yeah, but anyway, so this is a factor of the length or how large. So the larger the x is divided from the baselines, the larger the integrity, right? Okay. Okay, you keep going on.
So the first property of the attribution method to follow is called conservativeness or completeness. So that means suppose we have an input x and we also have a baseline x prime, and then we can define the attribution vector as AF. So A1 would be the attribution of x1, and AN is the attribution of xn to the output. So if you find the definition is quite confusing, maybe we can just look at some example and you can get the idea. So the idea is here, for each random variable I, the attribution value, the sum of all the attribution should be the input, should be the output of your input minus the output of your baseline. So here, for example, we have gradient. So the attribution of xi would be just the partial derivative of f with respect to xi. So if we have an example of function f, and it is equal to the x1 times x2, then the attribution would be the sum of all the gradients, and it should be equals to fx minus x prime. But it's very easy to prove it wrong. So for example, we have a baseline of 0, 0, and if x is equals to 2 and 3, then the sum of their attribution will be 5, and it is not equal to the difference of their output.
So here, so getting the, so means at the point of x equals 2 and 2, 3. And so the what does the conservative, so I still, sorry, maybe a little slow today. So what is definition? So may I look into definition again? So I still somehow didn't grab the idea of the conservation.
The attribution, because we are talking about attribution method. So for example, we wanted to know the attribution of xi to the output. Then each of the attribution method will give us a value of this attribution value. But by this definition, to sum them, to sum all the attribution should be.
So attribution I, so we can do the sum of, so given the baselines and given this is input.
Input. This is input.
And so we find that there, when we see the difference of the when we see the difference of f and f baseline and f input, the sum of attribute should be, the sum of attribute should be the difference between these two. So it's more like a preserve. We want to preserve or maintain the change. And how do we calculate the attribute I? But I haven't got it right. So here I means the dimension of I. So,
here we have x1, x2 to xn. So the I just means
the actual I. The actual I, this actual I means AI.
Yeah.
Is actually just, so okay, so here you're using AI, but so this A actually means actual here.
Yeah.
Okay. So here the idea that it also somehow quantify the attribution. Suppose the change of the change of f from the f baseline. We're going to have such a property. Okay, please go on.
So, for example, in the case of gradient, the attribution, the A1 will be, so this is A1, right? And this is A2. So if we sum them together, it's 5. But by the definition, it should be 6, which is 2 times 3 minus 0.
Okay. So according to the definition,
very easy to prove it.
Understand. So here you are going to showing that how gradients does not conform to the property of conservativeness. Okay? Then you're going to show that how integral gradients and ICSE conform.
But for integrate gradient, we can get the definition here. They actually by the definition. So this is AI actually, and the integrated gradient is to sum all the AI together. So so by definition, they prove the outcome of the result of integrate gradient can equals to fx minus.
Can you write down a few equations there?
So AI is equals to this equation, right? So by add a sigma here.
So let me do the trick with your example. So let x equals xi, x1 equals x2, right? So basically.
Oh.
So this example. So do you have a calculation for the previous examples in your follow-up slides?
No. So basically, by mathematics.
Yeah, from the mathematics, because I still somehow is digesting these formulas. I somehow remember the formulas, but I forgot how I understand this before. So yeah, maybe using with a few calculations, I can understand it in an easier way. So it will be alpha equals 0 and 1, right? So maybe I'm right on myself. So,
okay, maybe we can use the example before, like fx equals to x1 times x2, maybe.
Yeah, so yes, the 2 and 3 here. So let's say that AI equals, so AI equals 2 and 3. So the gradients is from, so this part is actually alpha 1 to 0. So it should be the partial derivative. So if we're using A1, so it means this one is 3, right? 3xi. So the derivative here is a line. So this will be 3. 3. Am I correct? Let's because this always be 3. So this partial, this component will always be 3. The alpha. So it will be, but anyway, so 3 minus 0, 2. So attribute 1 is 6. Am I correct? And similarly, A2 is supposed to be 6. If we add it together, it's 12. So it is not equivalent as well. Hello, Xianglin, am I correct? Or do I have the mistakes in the mathematics?
Maybe I'm also doing the math myself, so I kind of.
Yeah, Ruofan, would you please do the math together to see whether the integrity gradients can conform to the conservativeness property?
Actually, I have a question here. So does this integral be equivalent to f prime xi?
Yeah.
Where xi is from x prime to x, or x to x prime.
X to x prime. Oh, x to
Okay. Is that mistake? It should be x prime minus x prime. Otherwise, when alpha is equals. So
yeah, I think it should be.
Yeah.
Yeah, I think you're correct. So this is equal to this one. So here is x prime.
Then this is just f evaluated at x prime minus f evaluated at x.
Yeah, so here that means, so it means that my calculation correct here. So giving Xianglin's giving definitions, the integrity gradients are not supposed to be conservative, and because it will still need 2 times this vector, right?
So this is 6. This is 6.
Yeah, 6. Because I'm just using because I have some trouble to fully digest this formula, so I just use concrete examples and do the integral calculation. So I just find that A1 is 6 and A2 is 6, and actually this conforms to your observation that for an abstract formulas, this portion is indeed fx prime minus fx. And given that Xianglin mentioned that the sigma of attribute xi should be equal to these vectors. So Xianglin, I like that the integrate gradient does not conform to the definition of conservativeness.
But it is.
It's supposed to. But giving this formula is not necessarily not. So what is the problem?
But here it has a factor in front, so 6 behind this factor.
Yeah, so it cannot be.
So one is 2 and the other factor is 3, so total is 30.
Yeah, so here the point is just here when we calculate A1, so this factor is 3, and this factor is 2, and if we're using A2, this factor should be 2, and this factor should be 3, right? It's still equals to 6.
Oh.
Right? Because the point is that giving this example xi times x2, and suppose we're using partial derivative, it is linear. So the partial derivative means that this x2 is a constant. Suppose we calculate A1, this x2 is constant. So fx is equivalent to 3x1. Right? And when fx is equivalent to this one, it means that the derivative, so every derivative over these equations is constant with 3. So in this case, because then the alpha 0 to 1, it means that it is 1, right? It's 1. So this factor is 3. And when we calculate the length, it will be, when we count the length, it will be 6. And Xianglin, have you finished the calculation? Have I made a mistake on the calculus?
I suppose not.
Yeah. So what is the problem there? So your argument is that the integral gradient is supposed to conform to the conservative property, but it is not supported by the mathematics.
Yeah. I didn't prove it myself, but
how about this? We do not linger on this part because we still have 2 presentations. But you keep it. You still work on it. Yeah. Okay. Please go on.
Okay. And for the, I think it's weird because for the average causal effect, the author said they do not conform to the conservativeness property, but from this equation, actually, I think it did conform to this property.
We still need to understand this because you are supposed to be, and after 3 or to 4 years, you're supposed to be an expert in this area. So you need to, and we need to figure this out. Maybe next slide, and you still need to work on this part.
So, and also the next property is called sensitivity. So that means if the outcome of fx is not equal to the fx prime, then the attribution of x should not be 0.
That's supposed to be okay. So yeah, that will be somehow understandable. And this, I remember this example is raised by the paper. Raised by the paper from integrated gradients, right?
Yeah. So here, for example, we have a fx equals to 1 minus value 1 minus x. Then here, suppose our baseline is 0, 0, and our x is x is 1 to 1. So from here, we know that fx not equal to fx prime. But however, the gradient for x is 0 because it plateaus at when x equals to 2. So this can prove that the gradient method do not follow the sensitivity. Yeah, and the integrate gradient and average causal effect all follow this sensitivity attributes, because by the definition, for example, for the average causal effect, by the definition, if our xi is not equals to the baseline, then the average causal effect would not be 0, right? Just by definition.
Yes, by definition.
Because it says if our x is not equals to the baseline. Oh no, the outcome. So if fx is not equals to fx prime, then by definition the expectation of y, by definition,
why?
is equals to
Why?
the expectation of y when the input is alpha is not equals to the expectation of y when.
But it depends on the distribution of other x. It also depends on xj, right? Suppose, yeah, I understand fx. This factors is not equal to 0. But in this case, even the expression of y not only depends on, because this is a condition probability. So x equal to alpha, x equal to the baseline. And I think there's still a possibility that e, y, these two items can be together, can be the same, can be equal. Because it depends on xj. Suppose there is xi, suppose this dimension xi, and this another dimension xj. And xi equals to alpha, xj equals to xi prime, the baseline, let's say b. And we can also control the xj, right? Suppose it is suppose the final y is equal to xi minus xj, or whatever it is. So suppose when, and if we control the, if the distribution of xj is to be different. For example, when xi is equal to alpha, xj is equal to alpha, and when xj is equal to beta, it's equal to beta. So in this case, I don't know, but I think it's not that convincing. It's not that straightforward from my perspective. So for me,
but here we will talk about xj. If you only look into xi.
Because if we calculate, if we like to calculate the expectation of e, it still somehow depend on xj.
Or you mean other values?
Yeah, other values. And also, is there a proof for this formula? So that will
the definition. The definition is the how to say this? So if fx is not equal to fx prime, then this the difference between them would be not larger than 0, but it's not equal.
Okay. So
yeah,
this
so the attribution for x is not equals to 0.
But for this formula, it can improve, right?
So just by definition.
No, I'm talking about integrated gradient. When we go back to the previous slide, and these formula have been
yeah.
Right.
Yeah.
So that should be your proof based on some unproved fact.
This part maybe after my other presentation, and today I need to look into that because I kind of rushed to finish this and finish the other.
Okay. Maybe maybe how about I give you another 15 minutes to finalize your presentation.
Yeah. So the third property is called implementation invariance. So that means if we have two function f1 and f2, and for any x, the f1 axis equals to f2 x, we said this two network is the same in terms of functionality. Then the attribution method for f1 and f2 should be the same. That is implementation invariance. And all those three methods satisfy this property. So when I read the paper, it says only in those situations where the gradient is not continuous, then this property will not be satisfied.
Let's arrange another meetings. I will not raise questions anymore. Please go through your presentations. I think you need another additional presentation for this. Please go on.
You mean we need to arrange another meeting for this?
Yeah, we need another arrangement. Yeah.
Okay. So the fourth property is called symmetric preservation. That means for a function, if fxy is equal to fyx for any xy, then the attribution for x and y should be the same. So also for gradient, it's very easy to prove it, not to confirm this property with this simple example. But for integrate, gradient, and average causal effect, they all satisfy this property.
But there's no proof. There's no proof. You have to provide a proof here.
Yeah.
Okay, please go on.
And the last property is called input invariance. That means if we have two functions f1 and f2, and for any x, the f1 x would always equal to f2 x plus c. That means we have a constant shift between x and
so
x.
This is f1 and f2 are two different networks.
Yeah, but f1 x would always be equals to f2 x plus c. And then the attribution for f1 x should be the same with of attribution f2 x plus c.
Okay.
Yeah, that's called input variance. And they did an experiment to prove the integrate gradient do not follow this property. That means here the input will be 7 and 6 and 2, the image of 7 and 6 and 2, and they add a constant shift to the image. And the middle one is the outcome of integrate gradient, this part. So when they add a constant shift to the input, the outcome of integrate gradient then becomes different. So by doing this experiment, they prove that integrate gradient do not conform to the input invariance property.
Okay.
Yeah.
I do have other questions, but I'm going to refrain myself to ask. So have you finished all the presentation?
Yeah.
Okay, so I'm going to give some comments here. So it's good that you have clarified what is 5 properties here. I think you have illustrated what is the 5 properties, but I do have the questions. But anyway, so overall that part is very clear. But the problem but you still have some rough. It's a little bit rough to why the property when I raise the questions, maybe you did not expect that me to ask, but I'm also always the one who asks. So sometimes if you feel that if you cannot, sometimes we'll address the question. Maybe we can delay your presentation 1 week later. So that is fine. But for now, I think in next presentation, you're supposed to giving these properties, and I hope that you can provide proof for every equations. And for next meetings, I think we do not give you have presentations on the group meetings. We may have some individual meetings, maybe put on the regular meetings, or maybe we have meetings together with Wolfgang, Wang Chao, and Wang together to have a detailed explain for this part. And why I speak on this, because the causality analysis for deep learning network is somehow related and relevant to the visualization technique. In the causal pixel and the causal inference can be further visualized as well. So that may inspire our future research work. So this part, I think, especially for deep learning debugging, deep learning visualization, these effects are also, those parts I think are basics. We need to figure this out and be very clear on this. Okay, let's think about how do we arrange another meeting for this one, and I can have a discuss with you later. Okay, thanks, Xianglin. Maybe next.
Okay.
Maybe next. So yeah, but I do suggest that when you prepare the slides, I do hope that you can well illustrate it. So I find that I feel that some parts you understand it very explained, but some of the other parts, when you get a bit confusions, I hope that you can spend more time to understand these. I understand that some parts you cannot skip it. Usually we do the presentations, we somehow will skip the part I don't know. But in this part, there's a very there's a crucial part. We have to illustrate and we have to understand. If you hide it, I will have to raise the question to ask whether there's some part and play an important role. In this case, I suggest that you spend more time. I suggest
Yeah, of course. I know. So
to understand this part and then
yeah,
digest it. Yeah. Okay. So the next one, how about Yihao? Yihao, will you please share your slides and we can start another presentation. Hello, Yihao.
Yes, I'm sharing the screen. Okay. Should I start?
Sure, please.
Okay. So the paper I'm going to present today is called Code Generation as a Dual Task of Code Summarization. And it is published in 33rd Conference on NeuIPS in 2019. And the author of this paper is again our old friends from Peking University and Monash University. So before going into the paper, let me recap again some background knowledge about code command generation. So code command generation is also known as code summarization. So later we will refer code summarization as CS. It is aiming to automatically generate natural language descriptions for source code. And we have three types of methods: template-based, information retrieve, and neural network. Currently, the most popular and the SOTA paper almost all use the neural network method to generate code comments. And we also have the code generation. Is aiming to generate code based on the natural language intent. So for this task, almost all the methods use the neural networks, which take a natural language description as an input and use the decoder to decode the description to a generated source code. And some other papers also propose to include grammar rules or structural information to improve the performance of code generation. And we will refer code generation as CG in the later slides. So here, code summarization and code generation is obviously closely related to each other because the input of CS is the output of CG and vice versa. And moreover, both can be solved by using decoder and encoder framework and some other points. Okay, I put a question here. Maybe can someone also identify other relationship between the CS and CG?
So other relations. So maybe let me ask. Aaron, is Aaron here? Hello, Aaron. And how about Xuezhi? Is Xuezhi here?
Yeah.
Yeah. So here we have two problems. One is code summarization, and one is code generation. And Yihao has already shared their two relations between these due tasks. The first is that the input of CS is output of CG, and vice versa. And the second relation is that both can supposed to be supposed have a structure or have the potential to be solved by the decoder encoder framework. And can you identify the other relations between CS and CG?
Give me a time. So both the task to encode semantics, right?
Yes, that's correct. And so you mean that both the code summarization and code generation tasks will encode the semantics of input, is it?
Yeah, I think the model is aimed to try to learn the semantics.
Yeah, that's true. Yeah. So there is no standard answer here. You can name any relationships that make sense. Some other relationship, including like Xuezhi just now said, they need to understand both the model, like the decoder encoder framework needs to understand the semantic of natural languages and also the structure or the semantic of the source code.
Yes.
And here we also introduced the concept of dual learning, which is applied by this paper. So dual learning is a reinforcement training process that jointly trains a primal task and its dual task. So this primal task and the dual task should be related to each other, like we just said, the relationship between CS and CG. And this kind of technique has been applied in many different areas, like machine translation in both ways, like from English to French and French to English, and also the between the question answering and the question generation, etc. So this paper is adopting the dual learning to learn to train the code summarization and code generation at the same time as a dual task. And we introduce some notation here first. We denote the set of source code snippets as X, Well, the xi is the token sequence of the code snippets. And also we have the, so X means the source code, and Y here means the corresponding natural language commands. So here, the superscript I are one-to-one correspondence. And the CS model has a mapping function from X to Y, and CG model has a reverse mapping function Y to X. Okay. And this paper designs a dual learning framework to train the CS and CG model simultaneously to exploit the duality of them. So you can see here is the overall framework for training the code summarization model and code generation model at the same time. Here I will use this graph to illustrate a bit about the overall framework, and later I will go into details of each component. So here the code summarization model here is using a decoder and encoder, and similar for the code generation model. They both use the sequence to sequence encoder decoder model, and the basic units they use are the bidirectional LSTM with the attention mechanism. So to apply the dual training, they also incorporate some penalty terms on the loss function, which is known as the dual constraints. So later we will go into details about how they incorporate those penalty terms. And we can see here that the code snippets is the input of the code summarization model, and the output will be the code commands. And vice versa, the code commands is the input of code generation model, and the output is the source code.
Sorry, Yihao. So here I have a question. For the traditional trainings, whatever we generate code or generate comments, we always the loss function is defined by comparing the generated comments and the real comments, and vice versa. The loss function for code generation is defined by the generated code and the real code, right? Or the real code. But what is the benefits for using these dual trainings? Because in a training set, isn't it better to compare the real code? For example, when you generate the code comments, and what's the benefit to using these dual trainings?
Oh, here we during training the training process is still supervised. So for example, for the code summarization model, the input is the source code, right? And it will generate the code commands, and it will compare with the ground truth code commands.
Okay, so it still compare with the ground truth. And
yes.
what benefits does this dual training bring us?
So the main thing is it has incorporated some dual constraints to so in this constraint, it identifies some symmetry structure or the relationships between these tasks to put some constraints on the loss function of both training process.
Maybe do you have examples in the following?
Yeah, I have.
Okay, sure. Please go on.
Okay. So let's go into the code summarization model. So this is actually a very basic model, and it's using the bidirectional LSTM with attention mechanism to encode the source code. And one thing to note is that actually by using this model, it treats the source code as the same as the natural language, because it is only tokenizing the source code. And so the training process is token by token to be fit into the LSTM. And decoder is another LSTM to decode. And the process is formulated as the formula here. So here, if you remember, Y is the commands and X means the source code. So here the conditional probability means the given X and also given the generated or the ground truth Y before timestamp T. We want to maximize the probability of YT. And so by converting this formula into the loss, we get the negative log likelihood loss function, as shown in the bottom. And similarly, we have the code generation model. It is also using the same structure as the code summarization model. That is the bidirectional LSTM sequence-to-sequence model. And different from the CS model, the decoder in the code generation model learns a conditional probability as this. Actually, it's not very different. Only the input.
So
and the output
here, the code generation model still consider the code is a sequence of tokens, right?
Here, the code generation model will take the natural language as input and output.
Yeah, I understand. So, but still you can see it's XT. Each X is a token instead of you will not consider. But when we generate it, so in the very, very conventional code generation, so it will consider the code as a part of tree. So it will generate a code from the top-down level. So we generate the method bodies, then we're going to see what kind of states into there and somehow. But if you go through the tokens, it's still fine.
Yeah. So this is called the token-based method, and there's also tree-based method. And here we comes to the dual training framework. So the dual training framework includes the three components: the previously introduced CS model, CG model, and two dual regularization terms to constrain the duality of two models. And here we will introduce the first term. So given a pair of X, Y, X means the source code, and Y is the corresponding command. The CS model and the CG model have probabilistic correlation because they are both connected to the joint probability of PXY. So here, by the formula we just introduced in the last two slides, we can easily see that this equation holds. And we also denote the theta xy and theta ys as the parameter of CS model and CG model respectively. So here the conditional probability can also be represented as given the theta xy and the source code we want to compute.
The theta means the parameter. The theta, the theta means the weights or the weights of the neural network model.
Yes, the weights.
Okay, so parameter. So what the theta xy? What the difference is theta xy and theta yx?
They are So theta xy is the parameter of CS model, and
Yeah,
theta
so,
yx is the
so
parameter.
it means that the CS model and the CG model share the same parameters or using different parameters.
They're using different parameters.
Doing different parameters. So, yeah. Okay.
So we want to incorporate this relationship into a penalty term, into a constraint on the loss function. So here, how to explain this? Because we take the log, so the addition of log is just is the same as the multiplication of the inside term. So it means the px times the py pix theta xy, and minus this term, which is the same as here. So we want to minimize this L dual. So this is the first penalty term that we introduced to our loss function.
Okay.
Why there's a square?
The one to be positive.
Yeah.
So the minimize will be the minimum value is 0.
But if you take a square, then compared to the other normal loss, the penalty term will be large.
Yeah, but because we're using the Lagrange multiplier, so before each penalty term, it will multiply by a Lagrange.
Oh, okay.
Term, yeah.
Sorry,
so that will come.
May I ask a bit, what kind of, can you share example of Lagrange multiplier?
Later I will.
You will share.
Yeah.
So the basic idea. So here the key insight is that there are the formulas. So px times pyx equals py times pxy. So by this means, if we change two models, there's supposed to be such equations here. That means when we see x, and we're going to predict y, and somehow means when we predict y, then we have a okay. What's going on?
Yeah, and here we will introduce the second term for the dual constraint. So naturally, structures of CS model and CG model have symmetries, meaning that the output of one model is the input of the other model, and vice versa. And this paper focuses on the symmetry of attention weights, and they speculate that the attention weights of the both model are in a similar sense. For example, if the code here is string.find character, and the command here is find the position of the corresponding command is to find the position of a character inside a string, then the papers speculate that the find in both the code and the command should have similar attention weights. So this is the idea of the second dual constraints. And to
similar attention weights.
Yeah.
Okay, please go on.
So to achieve this, the paper denote the attention of CS model and TG model before normalization as the AXY and AYX. And then we use BI and BI prime to denote the individual attention weights for each token. So I means the ICE token, and because AXY is the attention weight before the normalization, so we use the softmax of the ICE row vector of AXY to denote BI, and similar for BI prime. So here BI and BI prime are a probability distribution among the sequence of token, the input sequence of token. And here so the regularization term is given by the bottom formula. And here the DKL means the KL divergence. So it is to compute the difference. It is to measure the difference between two probability distributions. And here it means that it wants to minimize the difference between the BI, which is the attention weights distribution of the CS model, and BI prime.
Sorry, Yihao, let me go through the previous slide. I still have some questions to ask.
Okay.
So here we start with intuition, the strings or fine. So the theory is that given the code, we generate comments, and given the same comments, we generate code. And the intuition here saying that the token fine should have the same weights in both in the code and comment. If it is the code here, if it's going to have the same weights, it means that in the code, you still need to take in the tokens in the code. They still share the same embedding technique. Am I correct? They share the same embedding. So even for the string, or even for a name string, even for the name of the code, there's supposed to be a bad model. Please correct me if I'm not correct. So giving these tokens will become the sequence because you use this bidirectional STM to do the job, right? So suppose this code will look like this, and there's a tension here to calculate all the weights. And the fine and this fine and fine are using the same embedding. Am I correct? Should be aligned with the same token fine in the source code. And those fines should be aligned. And how do we know these two walls are aligned?
Okay.
And when you describe the B here, I still get a little bit confused with the KL divergence. You're talking about what kind of probability? Maybe next slide. So I need these questions here. Suppose the clear tension weights. Yeah, and how these attention weights will be aligned.
Yeah, maybe I can answer the first question first.
Okay.
So just now, actually the attention weights here is the attention weight between the encoded input and the decoder. So that's why here we have a matrix of A, X, Y, and its dimension is n times n. So n is the length of input source code, and m is the length of output commands, and AXY represents the attention between this between the input source code and the commands, and vice versa for the AYX. So here AXY and they speculate that the AXY and AYX are symmetry, or they are in a symmetry.
So the point is that so let me rephrase will you please go back to the previous slide?
Yeah.
Your point is that this token fine so this token fine compared to the rest of the code should have a higher contribution to this find. And this find compared to the rest of the tokens should have a higher contributions to this find and the code. All right, but here for this code, it has only 1, 2, 3, 4, 5, 6 tokens. And this one is supposed to 1, 2, 3, 4, 5, 6, 7, 8, 9 tokens. Right? And how do we make such a, so anyway, so here was, as you mentioned, it will have a 9 and 6 times 9 matrix. And suppose this matrix, if 6 is found here, and suppose it's found here, and for these rows, it might have, suppose these rows might have 0.5, and the rest some are 0.5, and this something like this, right? So that means, and for this one, for this columns means that for this S, it contributed to the different tokens, and this is code and this is comments. Something like this idea. Okay, please go on.
Yeah. So here, the B prime will take the ith column vector of the AYX to have the symmetry vector, and we can formalize the regularization time by the bottom formula. And just now you say you have a question about the KL divergence.
Yes, BI is a probability of of token I. And what is so how do you assume BI prime? BI prime is the
So it takes the average of BI BN prime to ensure that to get the average of distribution.
So BI means let me see. BI is the ith tokens in the code contributed to different comments. BI prime means the ith token in the comments contribute to different code.
No, because here the AYX is taking AYXI is taking the ith vector of the AYX matrix.
So BI is still okay. So BI is in another model. Maybe it's for BI is for CS model. BI prime is CG model. Okay. So the KL divergence. Why is this using average? Why not just using divergence of BI and the BI prime? Right? By right, it's supposed to be BI and BI prime. It's just more intuitive way.
Yeah, but my understanding is that maybe they don't want some effect that maybe BI becomes the BI prime or BI prime becomes the BI. They want somewhere between BI and BI prime. That is the average of BI and BI prime. That's my understanding. So if you just put the divergence of BI and BI prime to be as small as possible, they maybe the BI prime will not change, and BI will be converging to BI prime, and that's not what we want.
Okay.
So after we define the two dual constraints, here is the overall algorithm, and here we have the mini batch of xi and yi, which is our training samples, and we want to calculate the gradient of the theta, which is the parameters of the CS and CG model. So here, g, x, y, and gy, x denotes the gradient of the loss function. So here the loss function, for example, xy represents the model of code summarization, and we have the normal loss term that we defined, and the first dual constraint and the second dual constraint. So we want to minimize this terms, the sum of these three, and we minimize the loss term of both models together in each iteration and update their parameters together. So this is the overall algorithm for the model.
Still have a small question. So when they calculated the symmetric matrix, so they first using the probability, so the probability constraints as the first loss, and the second they're going to calculate the counter attribution. Oh, sorry, the attention matrix.
Yeah.
For the attention matrix, so it's the loss is added to the attention, right? So attention, and giving the attentions, it will be so the attention is always be a matrix.
Yeah.
Okay, please go on.
Yeah, because in the encoder-decoder framework, there are two types of attention. One is just inside the decoder, in the encoder. So it's the attention between the inputs, and there's another attention in the decoder, which is the attention between the inputs and the outputs.
Okay.
And they use the latter one. And so they have done the experiments on two separate data sets on Java and Python. And here is some statistics of the data sets. And the results for the code summarization model is presented here. We can see that some strange point is that they are, even with their basic model, you can see here, the result here, even with their basic model, their result is already quite good compared to the other baseline they have chosen. And here in the paper, they have given some reason saying that compared to the sequence-based model, the tree-based model is not does not have strong performance. Maybe because after the source code is converted to AST, the number of nodes becomes very large and resulting in increased noise. But this reason is not quite convincing to me.
Oh, by the way, so is that possible that we still get their model for this code? Because I'm not sure whether this is an appropriate baseline, but is that possible that we also train this? But of course, this is pure comment generations, and then our target is about the comment modification. Maybe let me think about it later. Please go on.
Okay. Yeah, they indeed choose some state-of-the-art baseline method, like the API plus the code. Is another paper that I have read. And you can see that by using their dual model, the result is quite good. And this is for the code summarization model. And similarly, for the code generation model, they also compare to some baseline models. And here the POV represents calculates the percentage of code that can be parsed into AST.
Let me see. So it means that for the dual models, the dual model means both for generating comments and code, right? So only 30% of code have correct AST tree.
So yeah.
So it's also very preliminary research work, very hard to be impactful. Please go on.
Yeah. And they also conducted ablation study, and the results is showing in the table 4 here.
So what is ablation study?
Ablation study is they want to prove their they want to prove the various techniques they have used are correct.
Okay, so for example, it's not how the control experiment, right?
Yeah.
Probability. Okay, so anyway, so we have the we're going to see whether actually we got it. So it's more like controlled studies for two key features. One is probability duality, the second is for the tension duality.
Yeah. So they have shown that both the probability duality and the tension duality is necessary to be incorporated into the system. And the last is some examples that is shown in the paper. So A is the CS task and the B is the CG task.
So that's a task. We report that result. There is no code. So I'm still thinking about another way to look at it. So comments generations, but of course, that's all right.
Yeah.
Okay. So I have a few comments, maybe not for these papers, but for our research work. We can still keep thinking about the significance of work. So code comments is a very interesting. Comment generation is always very interesting. That means we do not need to write a comment on our own. So, but the comments generated, the generated comments were always for the future maintenance, right? Especially for some newcomers, especially for newcomers. And as for those code, like these examples, the close quietly. So for this part of the code, it's actually even without a comment, this part of code will be fine, right? It will be fine. And for us, maybe a more significant approach is that we're going to identify, because as a programmer, if I'm writing a code, I will not write comments for every piece of code. Only the code, the people, or even future me have difficulty in understanding this, right? So I think the first question for us to ask is not to giving an arbitrary code within generate comments. Those kind of comments, maybe a little bit monologue. A more detailed way is like maybe you can go through the comments itself to see that which part of the code is more important, which Java method or which method is more important for us to annotate the comments, or which portion of the code fragment is more important for comments. For example, if I'm going to generate comments, whatever it is, we always say that we check whether the variable is not equal to none, and then we do whatever it is. So this becomes very monologue. And I think the most important thing is that we're going to find the most important areas for us to generate comments. And then we're going to show how it looks like. So here, I think one argument for the significance of our proof is that we're looking to the code which has already annotated by the programmers, so that we believe those part of the code is actually more relevant to it's more important to have a notation. The second is that I think the code comments may not necessarily focus on the code, the Java method itself. So here is opinion that, for example, suppose this piece code utilize global variables. And somehow a lot of the logics just depend on these these global variables. In this case, if we just look into the message itself, we can maybe have a brief generate comments briefly. But if we want to generate the comments more accurately, we may need to analyze the structure. For example, what method it has been called, and what global variables it has been visited or accessed. By this means, we can extract more semantics. So in this case, I still highly recommend that we start with a few qualitative analysis. We look into a few examples and how humans or us should write comments. And suppose this logic is very complicated. What is the relevant code elements for us to reference? So all those parts are very, very important. We should, for this stage, we do understand those AI approach and the traditional software engineering models works. That is fine because they are working on the low-hanging fruit. So those low-hanging fruit, they just adopt, maybe they adopt, of course, they have their own customizations and novelties, but they may miss some very important key sites from the code perspective. And we somehow need to incorporate this perspective into our work. But also, we need to start with those comments first. Maybe you can just keep in mind that the first is that our work is about the code modification recommendations. So that will be refrained. And otherwise, suppose our chant, suppose, for example, we invoke additional methods or we remove additional methods and we additionally visit or access a global variable and how this additional access and how these variables and we also need to uh, look into the variables there. So maybe the machine learning approach will be an assistant, but somehow we need to develop our own models or define our own fairness, just like these papers, to enhance and provide our to address the challenge here. So I think for the current stage, by the way, have you finished the code examples? Have you finished collecting some code examples for how the comments look like, and compare the results of those compare the results of the real comments and the comments generated by those filter methods?
I haven't.
And right, so I think we should do this as soon as possible. We should do this as soon as possible. And maybe by next Tuesday, I think by next Tuesday, we the code clone is hard for you to work on, but for next meetings, I expect that we do have some results. Do you have results and how these models is predicted on certain code and what the code really looks like? And also, if possible, so I will give you some projects. I will give them projects, and these projects, and maybe you use your own projects. Have you ever written some Java projects?
Yes.
Right. So I think the first is that maybe you can start with the Java projects you are familiar with, so that you are the expert to know what is a real comment. Then you're going to see how this approach lack and how this approach does not have a good performance, and we're going to improve upon that.
Okay.
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 Thanks, Yihao.
Sure.
Then we supposed to have the last one, Zhou. Hello, Zhou.
Hello, can you hear me? Hello.
Yeah.
Can you hear me? Yeah. Okay. Okay.
Yeah.
Give me a sec. Let me share my screen. Oh. Okay. So I'll be talking about. Hello.
Yeah.
Wait, can you see which screen are you seeing now?
Yeah, I can see. I think this is. I think I see your another screen, I guess.
Yeah, I'll move this over. Wait. Give me a second. Give me a second. Let me fix this first. Sorry. Okay, got it. Okay, so today I'll be presenting on a paper automated web testing using curiosity-driven reinforcement learning. So it's by anonymous, so we don't know who is it by. Okay, so first I'll explain reinforcement learning for those that are not sure of what reinforcement learning is. I'll give like a very simple explanation and a very watered out explanation. So basically for reinforcement learning, you need the state. So in this example here, we have the environment, which is basically a grid and an agent. And so you need a state, you need actions, you need a reward. Here the reward is 1 if you reach this goal. A utility function, which basically what's the utility of the value of that state, and a reward function. Actually, sorry, the utility function is a reward function. Just ignore the utility function. I messed this up. And then you need a policy. So basically, what policy to take. So given a state, what action should you take? Okay, so let's just see how this works. So here, using this reward function, QSA equals to RSA plus. This is a decay, basically, max A, QSA. So basically, at the start, the utility is all the same. They're all 0. So the agent will just start taking random actions. So after he moves up, the utility becomes negative 0.01 because normally you put a negative cost to for each action, but yeah, it doesn't really matter. Then he will take a random action again, and then go right, take random action, and now you reach the 1 state, so we'll update the previous state as. So this up, down, left, right. So down will be 1 now. And then if you continue moving on, you start, then now you'll rerun again. Then you'll go. So now he will take, let's say he'll take any action from down, left, and right. But there's only one valid action, which is the right. So he will take the right action. And then we'll update the value again. Then update. Oh yeah, so here he will take the to the right because this has the highest QSA. QSA is the S prime. QSA, which QS prime A max A is 1 from this step to that step. Yeah, so that's basically reinforcement learning. Simply explained.
So yeah, so you have explained quite well. Yes, and there's an excellent animation here. So here, so that means for each state have an action. So is for here the actions just the value. So why this here is minus 0.01? So why we
okay? So, as in, it can either be 0 or negative 0.01, but normally people use a negative value to encourage it to find the reward faster and not just like run around in circles. But yeah, it can be 0 also.
Why if the so here it must be a reason of 0.0 or negative 0.01. So when,
I just decided that each step has a negative value.
When the engine was anyway, each state is position here, right?
Yeah.
Each state is positions, and the values on each position means the probability or the inclination to move up, down, left, and right.
Yeah.
And
the QSA, correct. So
and here, suppose 0 means all directions are almost the same. So
yeah.
It takes a random move. But what if it becomes 0.01? So it's somehow related to the formula, right? And yeah, also so when you are moved, you mark it as minus 0.01. So this value influence the decision making, right?
Yeah, correct. So as in okay, I probably should have change all this to negative 0.01 to make it more clear for like all these zeros over here. Yeah. That's
so here maybe can you go back to the first move you have?
Yeah. Okay. I think I should.
So
the reward function normally is else it can be either 0 or some small negative value that you set. So I just set it to 0.01, negative 0.01. So that basically is to encourage the agent to get to the end goal faster rather than just like walking around in circles.
The RS is one. Sorry, let me check the slide first. The RS is one if the action brings you to the final.
The final square is here, the bottom right.
0 or some negative value. Also, that means if we make a decision on certain state, if it does not lead to the final, if it does not lead to the final reward, it will be marked as negative 0.01.
Yeah.
So it means that, so it just indicates the agent, to tell the agent is that try to avoid these decisions a little bit in the future.
Yeah, correct. So it just basically tells the agent to get that. So basically there's a cost to traveling. So that if you don't want it to take the shortest path, you don't want it to go in some weird way.
For this case, maybe, so let me say, suppose the trajectory, the trajectory looks in such a way, right? So if they reach to the final goal, so, and I think we need to assign the reward for this track.
All right. So you'll be like this.
Right.
And
then here you only change this into 1, but all the other trajectory is still 0.01, negative 0.01. And isn't those state or this decision can still get a small reward? Maybe if I'm intuitively, this decision could be 0.5, and because there's a decay, and this decision could be 0.2, and this decision could be 0.1, and this decision could be 0.05. After all, if I make decisions here, I can finally reach the final goal. And then giving your state, every state is negative 0.01. So it means that, I'm not sure, it means that at the very initial stage, maybe in the next try, we learn the reinforced learnings. I will not go this direction anymore. Hello, Jingzhou, are you listening?
Oh, wait. Hello?
Oh,
sorry, I was muted. Hello, can you hear me?
Yeah, can you hear me?
Yeah, I heard you. So for Q learning, we don't normally backpropagate it. But then if you're doing like MTCS, Monte Carlo tree search, then we will backpropagate it. But it's just a code of Q learning.
So, okay, so this is actually Q learning. So for Q learning, so each time you go through the state, you just mark it as 0.01, and only if you reach these goals, you will modify. You'll just modify these ones, and all the rest was still 0.01.
Yes, correct.
And so it will generate a result that only this state and a state will be value of 0, and then all the rest will be have 0.01.
Correct. So yeah, so here
is that effective? Is that an effective strategy? And that means it learn nothing. Giving your description, it almost learn nothing in these scripts, because for these scripts it will end up all the 0.01, and only the state close to the let's call this as a successful state. Only the state close to those successful state will have a positive value.
Okay, so there are two reasons why you don't go update. So if you keep up, let's say if you use yours, okay, let me just change the slide so it's here, okay. So if you reach where we are, okay, here. So oh my god. So if we reach here and then we change it to, let's say this is 0.9, right? And then maybe this is 0.8. And then this is 0.7. What will happen here is that for the next iteration, we will continue to go by this way again.
I understand. So you need the diversity.
Yeah, you need diversity, yes.
So suppose what if we change it into 0.1, 0.5, 0.2, and 0.1. So it becomes a very small numbers. So when we do the random sampling, it still give a chance for here. It is still possible, right?
Yeah, as in so if you do this kind of like backpropagation, we normally call it a multi-color tree search rather than a Q-learning. So that exactly is actually multi-color tree search, which so that they will choose a node based on whether the node has been explored, and then they'll backpropagate it along the whole node.
Okay, so whenever, yeah, I understand. So here, I understand. So here, you illustrate these reinforcement learnings. Maybe I will go through more details of Q-learnings and multi-color strategies. Please go on, and to see how these how the authors apply these reinforcement learnings on the web testing. Yeah.
Okay, so let's move on. So why do we need reinforcement learning for web testing? So web testing are often difficult to test due to complicated applications and wide range of implemented languages like JavaScript or HTML or whatever. So existing approaches commonly use model or random-based approach, but suffers from various limitations. Like you basically have to manually create these models for each website that you want to create, and it may not be as diverse. So given a agent, which is the model that you're trying to create or whatever, and given a website, we need to find what is the state, action, reward, policy, and the reward function to use. Actually, sorry, the miscomplication. Okay, so we need to find the state, how to represent the state, how to represent the action, how to represent the reward, and the policy. So actually, what are these three? Actually, it's called a Markov decision process. Yeah. Okay, so normally what people use for states are image or HTML code. However, there's a problem with using image or HTML code is that if you use an image, if you make a slight modification to the site, say like if it was a database management site, and then you add a row, the image should be completely different from the previous row, even though the states are very similar. And then this leads to you having an infinite.
You mentioned the web page screenshot.
Yeah, correct. So I'm just saying possible states to use. Yeah, but what's the problem with using image is, for example, if you are given a website that is let's say a database management tool or something like that, and then if you add in one additional row of data, you have a different image and a different HTML code, right? And then you have another state, and you don't have many states because it's exponential. The more states you have, it basically creates a state, what they call a state explosion problem. Yeah, the explosion problem. So instead of using image or HTML code, they propose using this as a state. So the intuition is that HTML page that focus on the same business logic should be consolidated into one state. If two pages have the same URL and their HTML are very similar, they're likely to be focused on the same business logic, and they use this G-stop pattern matching, which they don't really talk about it's based on some other people's work. So let's not talk about that. That's not important. But basically, it's just how similar the HTML are. So for the actions, what they propose is that each action is an operable DOM element, such as a link button or input box, in which the operation may result in the changes of application status, X submitting a form or URL jumping or whatever. And so the reward function here is to encourage the goal here is to encourage exploration, not to find some kind of like optimal path. Like say if you're playing a game, you want to get from A to B as fast as possible. So they suggested a curiosity-based reward function, which is given here. You can see this. Basically, this value is initialized to 1, and each time state S prime transits to S by performing the action A, the corresponding this one is increased by 1. So that means basically the more times you go into the same state, the less the reward goes.
Yeah, the less curiosity we have.
Yes, correct. And this is the their Q learning update function.
Mm.
Their update function. So basically the reward is given by curiosity state prime A plus Q max A prime state A prime. Yeah.
Mm.
I think they sum up the reward. Yes, correct. So here they will sum up the reward over all the states to see what it is here. Okay. So based on the Q function, the policy they construct measures the weight of the valid action in a state S using the Gumbel softmax method, where A is a valid function at the state S, and okay, just basically the Gumbel distribution. So okay, actually this is just a softmax distribution. So normally why people use this Gumbel function, right? It's because you want to take the action with the highest reward, correct? The highest QSA. So normally I'll show you. Wait, sorry, let me go back.
So here is the policy when we learn the reinforcement learning policy, or when we really adapt the reinforcement learning when we're using this policy. So it is used as learning, or it is for training.
Sorry?
I mean, for these actions, for these policies used for training or used for working on the real scenarios.
So this policy is for you to select an action. What action to take?
Okay, so here
so
they're almost the same.
It's basically a softmax distribution. So they choose the action with the highest reward function based on the softmax distribution. But okay, so normally people use this Gumbel softmax because basically the max function is discrete and the max over action is discrete and non-differentiable. So people use this Gumbel softmax to make it differentiable. But honestly, I have no idea why they use it here because they're not even training a deep neural network. So I have no idea why they use a Gumbel softmax.
So it is not a deep reinforcement learning, it's just a reinforcement learning.
It's not. Yeah, it's not deep reinforcement learning. So I have no idea why they use this Gumbel softmax function.
Well, the problem is that if it's not a deep reinforcement learning, so the IL problems will always have a state problem. So and also for these web page applications, and they're supposed to have a lot of web pages. Even if they have state merging algorithm, there's still supposed to be a lot of states here, right?
That's why they simplify the state representation.
States representation. So
they reduce the number of states by putting sites that have similar logic together, so you won't have that big state explosion problem. As you have a bit, but not as much. Actually, like I think this paper is more like a Monte Carlo tree search rather than like reinforcement learning. So, but they just like to call it reinforcement learning. I have no idea why, but it's more like their method is more like a MTCS search. Yeah.
Okay.
Okay. So let's I have an example here. So 0 is a root state, and basically we start from the left. These are actions. Each arrow is an action basically. So at the start, because they're all initialized to 1, right? So the probability of choosing this one, or this one is the same. So you just randomly choose. So now let's assume that it just chooses. It goes like this. And then so you after you discover state 3, you update the reward function of state 2 and update the reward function of state 1. And then now because you increase by 1, so the reward goes down. So you explore the other state. Yeah. Basically, that's the idea. So actually, this is like an MTCS. It's not. I guess they use the Q learning part of it, but like it's more like, to me, it looks more like Monte Carlo tree search rather than like deep Q learning or whatever. Okay, so what's the problem here? The problem here, right, is that, for example, if you're given a form that has 10 fields with one submit button, right? You need to fill up the form. You need to give action from 1 to 10 in exactly the same order. You cannot submit and then fill in or whatever. You must from 0, 1, 2, 3, 4, 5, 6. You must fill in the form in that order, correct?
I'm sorry, I missed it. So will you please say it again?
So if on a web page, normally, let's say you have a form with 10 fields, correct? You need to fill in the 10 fields first before you click the submit button. So if you randomly choose an action to do, the probability of filling in 10 fields and then clicking the submit button is very low. Correct?
Yes.
So they propose this method called a DFA guided exploration, which honestly, I don't understand how it works. So I was hoping that you could help me with this. So I quoted out the relevant parts here and hope we can read it together. So a DFA is a deterministic finite information. Is a state of 5 tuples, where S is a finite set of states, A is a set of actions, and what's called delta is basically the cross of state and action. And F is a finite set of states that cannot be transited to other states.
So this is transition, right? Okay, the transition will be. So the point is that the transitions will be created. So the state machine is growing during the exploration, right? Basically, velocity driven trace selections from the DFA. We first select the transitions with the highest velocity, and then we adopt the digestion algorithm to identify the shorter path to trace that can reach to the target. So how do you define a target?
The target is like the next state they want to get to, I think. So they want to get to a different state. You want to find a series of actions that somehow get you to the next state.
But I install to the target transitions intuitively. Some transitions can be very deep and that's difficult to reach by DL. For these transitions, we explore leverage the DFL.
Yeah.
To further enhance exploration efficiency testing.
So I don't really understand how does this help the exploit the problem that we previously had.
The goal is that it's going to fill in 10 fields and click a button, right?
Yeah. So how does this help with that? I have no idea. Can anyone help me? I've read this actually 4 times.
We first selected transition. So here, I think this. I'm not sure whether you have copy and pasted the correct word or paragraph here. I think the major idea is more like this. So anyway, so we have a state tree like this, right? Suppose we have a state tree like this. And the idea from my point of view, suppose let's have a maybe deeper have here. So so the point is that if we want to, the goal of this web GUI testing is trying to explore the unexplored web pages or the unexplored states, right? So each time we will start from the initial root, right? Each time we start with the initial root, but it is actually a waste of time and effort each time we start with the root. So I think in this case, it will try to explore the unexplored state for maybe those are the leaf nodes. If this what I understand. So if we can start with those leaf nodes, it means that we have more chance to explore the unknown states. So here, those state machine, the FDFA is presented by such a state machines. And from its description, it seems that the transitions are always updated, right? So once S prime and S is exploited, so that means we find a new transition from S prime to S. So we will still add a new transitions. And for here, you can see for this sentence, from DFAs, assume that we are, and for this sentence, so I just speak what I understand. So suppose this is Sm plus 1, and this Sm, and this is A, right? So in this case, it's just going to, so the idea is that it's going to start exploring from this Sm plus 1, the state Sm plus 1. So in this case, it will just calculate the digestive algorithm from R to Sm plus 1. So that's what it explains, that RFF can directly store. So it will just apply the actions X1, A1, A2, A3, and 4. So by this means, it does not using the existing policies to explore the otherwise. It just calculates the shortest path and apply the actions along the tree. Then it's going to reach Sm plus 1 directly.
But how does it? So, but how does it help you with?
I'm not sure whether this paragraph can address the problem you mentioned, because the problem you mentioned is that this, suppose there's a form and it has two fields. So that's your problem, right? You need to input a username, input a password, and click a button. So if we just clicked add the usernames and do something else, then it will be always stuck on these states, right?
Yeah.
So somehow the challenge here is that there is a sequence of actions to trigger another state.
Yeah.
Yeah. Somehow, so if we use
unless they randomly do it, but then there'll be like so many things. It will be like exponential, right? If they just randomly try all possible actions.
If we are going to do this, one strategy is that we heuristically identify the form, and then we fill in all the fields in there and click the button there. So in this case, we somehow encode the domain knowledges into this state, and we can do this stuff.
Yeah. Maybe that's what they do. So okay, yeah, that's so that's so this is the overview of the this is the overview of the web explorer. Basically, they extract the state and then they just interact it, and then they just basically they're just using a Monte Carlo tree search to explore.
Will you please go through the workflow again? So start from
okay. So given a website, they will extract out the state. They'll find, given a page, they'll find what's the state. Okay, and then given the state, they somehow they update the DFA. And then they'll so if they require high level DFA guidance, they will basically okay, so I don't understand what this part is doing, but basically what they will do is here they will use the policy to select a state to update the model, select a state, update the model, and then this will give it the policy of reward to update the policy, and it will go back again. The next action after the next action. Yeah. So somehow this high level DFA guidance generates an action sequence that allows you to, that's the part that I don't really get. Maybe.
Okay, so no worries. Keep going on. I think the goal of this paper is just to trying to explore more web pages in the website, right? So using the ideas of exploring this one. Okay, please go on.
So okay, so now I'm just going to talk about the experiment. So they just had an experiment to investigate 4 key research objectives. How far does it explore in terms of code coverage? How effective is it in detecting failures of web applications? How effective is DFA in guiding exploration during testing? And how effective is Web Explorer in testing real-world applications? So this is their setup. They use 6 popular web testing GitHub projects as benchmark and tested it on 50 real-world applications and 1 complex SaaS software. So this is their results. Sorry, I think it was 6 real world applications. Like, yeah. So this is the other 4 benchmarks. Yeah. And
so each entry
is
the code coverage.
Yeah, this is the branch coverage, and this is the number of failures they get.
So how do they identify the failures?
So failures, they detect it by like HTTP status code. So if you encounter a 404 or something like that, then they will consider it as a failure that they found. So yeah, the goal is to try to find as many failures and cover as much code as possible. So this is what they got. Okay. So they also wanted to find out how effective DFA was with or without.
Sorry, I'm going to recap a little bit about their state define. They just purely use HTML, right? They're using HTML elements.
Sorry, which what am I talking about?
I mean, defining, say they're using reinforcement learnings. When they define a state, they're majorly based on they define the similarity, or they define the state similarity based on the HTML element HTML similarity.
Yes, correct.
Okay.
So
because they are testing a single web page, I think the HTML similarity is reasonable. But when we are looking into the phishing website, different phishing website may have different HTML code. So this makes the state. This may have a new requirement for us.
As in, okay, I'll talk about that relation to our own problem later, but let me just talk about this. Sorry. Yeah, so basically, they just show that the DFA helps them find more failures and give them better branch coverage in a shorter amount of time. Basically, that's what they're saying. So, okay, the question is, how is this relevant to our work? I think honestly, like this is a bit of over engineering if you want to apply it to our work, because most phishing pages are like just like 2 pages. So it's easier to just explore every action exhaustively rather than to do this. So it doesn't really make sense to have a whole like reinforcement learning network to do this rather than just do everything basically.
Well, here the problem, I'm not saying that I'm sticking to reinforcement learning. The point is that we need to reference the existing interactions, the benign interactions with existing phishing interactions. And somehow we still need to do something similar, like to abstract the state. And do you remember that when we have an interaction, as long as we have interaction, we still have state, we still have action, right? And we still have state machines. The only difference is that we may not need to store so large number of states. We just need to now transfer the states. That might be enough. So in this case, I'm not sure whether you have finished your CA report presentation, but for giving my comments, I find they somehow ignore my comments. Some comments are fine, but some of the comments is kind of important. I will mention this. So when prepare your slides, especially.
Sorry, I can't really hear you. Can you?
Yes. I'm saying that especially when you are especially when you prepare your CA reports, I find some of my comments is a little bit ignored. So I remember that when you prepare your CA presentations, I mentioned that you need to show the interaction, the sequence diagram. Do you know the UML sequence diagram?
Yeah.
Yeah, you know that, right? So you need to write this sequence diagram. And also there's always a automated tool to transfer the sequence diagrams to the state machine. Remember that different users, different agents will do different actions. And after they do certain actions, they will have a state. But of course, in our applications, for example, if we interact with PayPal website or interact with Facebook website, we also will have some states. And also you mentioned those kind of states. And we usually need to automatically extract those states and those interactions, and then we interact with a suspicious or unknown website. So anyway, our approach is a heterogeneous approach or a pipeline approach. We still based on assumption of Fishpedia. So once the Fishpedia or maybe raw Fishpedia, Fishpedia plus is finished, so actually our approach is one step further. Once we detect these two web pages are very similar, or is highly likely to be efficient, but we still need to adopt the interaction approach. Just what we mentioned, finally, that we found a PayPal website. We find this PayPal website is somehow conform to the PayPal layout. Even for that, we still need to try to interact with this website a bit. In this case, how do we do this? And we usually adopt compare to interaction model to see whether interaction is the same, right? So somehow I hope that for your CA report, I can see the sequence diagrams, maybe with PayPal, maybe with Facebook, and then you could just create another sequence model or the interaction models, and then you can just list in your slides and how these two interaction models looks like. So you can just say that for the plausible fission, and plausible fission is just the false positives. For plausible fissions, after we interact with those websites, we find these behaviors is almost the same with benign or legitimate website. On the other hand, if we are interacting with the phishing website, for example, we input the username, etc. We definitely here we define the policies, we define the actions, and we find that the feedback is different. In this case, we can find that if we interact, and also you can mention that how long do we expect for these interactions, or how long this interaction will last. Maybe it will just have interactions for 30 seconds or 20 seconds. We can build interaction models. And finally, we are comparing two models. We interact with the benign or legitimate website, we will have interaction models. And we interact with unknown phishing website or plausible website, and we have another models, we have another interaction models. And finally, we will propose interaction model differencing or comparison algorithms. And then we can further confirm whether those models are, whether the website are benign or malicious based on these based on our comparison. Hello?
Yeah, sorry. Sorry. Yeah. Okay. Yeah.
Yeah. So here in CA presentations you can have such a claims, and moreover, I think you can also prepare. I think another point I mentioned is that you're going to prepare the statistics for the prevalence of those kind of plausible fissions. I think you have tried a lot, right? So suppose we relax the requirement of the web mails on Microsoft Office or PayPal's, but you still need to keep in mind that given the PayPal web page, even if it is benign and the interactions, it's very hard to capture the interaction model because all these interactions is not the same with a legitimate PayPal login web page. Am I correct? Right.
Yes.
So somehow it's almost like isomorphic, find an isomorphic graph. So let me raise examples. Suppose this is, I'm now writing a legitimate interaction, or I'm writing an interaction model with a legitimate website. So suppose S0 means that the first stage we log into the login web page, and then we jump into S1. That means another web page. So we have username, password input, right? So suppose this is a correct username password, and we will have incorrect username password becomes S2. And what if we are keep input 3, or we deliberately input 3 wrong password, and what's going to happen? So that may be in 3, and maybe this state may be directly jump to another state. I don't know. So this is the interaction model of legitimate website. Now, okay, so suppose the web page is still a login web page. we can compare these two interaction models directly. Am I correct?
Yeah.
Yeah, so I'm not sure here. So maybe there's some probability. For example, if we have these actions, it may have a probability. It maybe have 30% of, it maybe have 80% of accuracy probability to jump to this state. It may have another 20% of accuracy probability to jump to another state. I don't know, but we need to interact with this model for a few times to know these ideas. However, if we are interact with another BNI website, so this BNI website, if I remember correctly, the domain name is IP address followed by some weird URLs .html, something like this. But if we adopt interaction model, we'll find that for S0 for this S, it's not a login page. So let's talk about S prime. And once we click the buttons, it will jump to S prime 1. We click another buttons, we jump to S prime 2, right? And from S prime 2, so we will have a subgraph. Suppose it is a BNI website, then it will jump to S0. S0 is actually a BNI website, and it will have a lot of interactions here. So somehow like this. So the real interaction is more like this. And it is still also possible that there's still a lot of S3 prime, S4 prime, because this website could be very complicated. As long as we click the buttons, we will find a new state here. So in this case, if we purely compare this legitimate interaction model M1 and this interaction model M2, it actually are two completely different interaction models. However, if we compare a subgraph of the interaction models, we can somehow know this, right? So in this case, I'm not sure whether it's possible. My point is here. So in this case, we would like to remove those irrelevant states as much as possible, because those irrelevant states cannot allow us to, those are just noise. We need to ignore them as much as possible. In the meantime, we would like to reach this state as soon as possible. So as long as we find this state, and we can match this state back to this state, and we can influence the BNI website already, right?
Yes.
Right. So in this case, I'm not sure is this possible, but a feasible solution is that if giving a BNI website, suppose we think it is a PayPal website, so we will try to find a way. This way may not be reinforcement learning, maybe some heuristics. So we would like to find a sequence of actions so that this website can jump to the login web page as soon as possible. Somehow there will be a policies, but if that heuristic is not so clear, we might adopt the machine learning approach to do the trick. But if the trick or these heuristics are very simple, we can simply adopt these heuristics to quickly jump to these here. So we still need to. So maybe in recap, giving an arbitrary BNI website, we still have 2 steps to go. The first step is that we need to find a sequence of actions to allow us to quickly reach the login page, right? Yeah. And then we're going to, if we already reach a login page, and if this login page can corresponding to a state in the BNI sequence, we do not need to explore this. Otherwise, if we still unsure, we're trying to generate these interaction models here, and we compare these two interaction model. And the first step, and for this first step, I'm not sure. Maybe you can try it a bit. And how do we address these? How do we address these problems? How do we, from the giving arbitrary models, and assume we have already reported it is as a PayPal or Facebook web page? How do we quickly explore the login pages as soon as possible and reach there? And I think if possible, if we can have a unified models, maybe reinforcement learning, so maybe something else. So that will be interesting. That's very good for us to explore.
Okay. Yeah.
Do you have any questions? If you have, you can just mention this, your concern.
Actually, my plan was to for the first part, right? This part over here, to explore the thing, right? Just use a web crawler and then just click everything. That was my plan. Click everything until you find a login form, and then you will feed it into the testing tool, because the testing tool is slow because it is.
Then how do you define? Then okay, if you would like to click everything, and how do you define we have already found a login page?
How do you define? So initially we can use the HTML elements, but in the end we were going to use the computer vision approach to look for interactable forms, basically.
So this is a tricky part. You can explore. Another comment is that you mentioned that you have finished the CA report. I have go through your CA report. It is fine, but I think the final result actually will be different. Will be a little bit different. You still have a large room to improve and add some new contents in your final report.
Yeah.
Okay.
Yeah.
Okay, that's all my comments. And I assume that you are quite busy for these 2 weeks, right? So when
I got a lot of time.
Yeah. So when will you resume this FYP project?
So 2 weeks later.
Two weeks later.
2 weeks later.
So it's assumed to be by the end of this month.
Correct. Yeah.
Okay. Okay, that's fine. I think we have enough discussions, and thanks Xianglin, Yihao, and Qingzhou giving good presentations. And let's meet in next Saturday. Thanks everyone. Bye.